Steve. I really appreciate the opportunity to talk to folks who are part of the stat division of ASQ. Um, as Steve mentioned, my background is as an applied statistician, so I'm going to keep this talk very applied. There's not going to be any math in there. There's not going to be any equations. As it turns out, a lot of the preliminary steps that you need to get involved in prior to applying predictive modeling techniques are very non-statistical in nature. Things like data cleaning and certainly preparation of the data tables, organization, and so on. So we're going to focus mostly on that. There are some. It is helpful to have a little bit of understanding in terms of what some of these techniques are looking to do. It helps you when we talk about things like adding additional structure to the data set, say. All right, so let's go ahead and get started. By the way, just as a point of logistics, I am going to. I've got the chat screen open on one of my monitors. I'd like to stop at periodic intervals and answer questions if there are any questions. I'd like to take this relatively slow. I don't want to speed through everything. I'm going to have some examples. Hopefully, I'll be able to get to those examples. As it turns out, almost everything that really I'm going to talk about can be done regardless of what software package you use. Now, even though I work for JMP and I'm going to show some of my examples in JMP, and hopefully I can work a little R in there as well, this can be done regardless of the package. Most of these packages have techniques that will enable you to accomplish some of these methodologies. So go ahead, let's get started with answering the question, what is data mining? A while back, I was asked to give a talk on some of the key concepts in data mining, and I like to start there so we have an understanding of what is predictive modeling and where does it fit in the context of data mining. So the first, I think of three different areas that data mining encompasses. The first is evaluating future observations, and those observations can be vector or scalar in nature. And here you know what you're looking to target. So you know what's correct, you know what's close. That's the importance. I am trying to come up with a set of inputs, a set of structures that would allow me to predict future observations. So that's one part of data mining, and that's really where we're going to be spending most of our time when we talk about predictive modeling. The second part is devising a set of rules for classifying a current or future observations into groups or as anomalous. A couple of different ways I might be able to do that, things like market segmentation, market basket analysis. In this case, I really don't know what my target is. I am just trying to use some sort of techniques to put things in buckets. And sometimes that bucket could be a very, very small bucket, things like outlier screening, intruder detection on internet, things like that fall into this second bucket. And then the third bucket that I think of when I talk about data mining is optimizing a sequence of events. A lot of this stuff falls under the guise of operations research, things like the traveling salesman problem, logistics planning, how do I create some sort of self-driving car, something that is going to sense aspects of the environment and self-correct for them. So that's another part of data mining as well. And part of what I'm going to be talking about can be used in some of these other aspects of data mining, but really they're specialized to predictive modeling, because what they're attempting to do is they're attempting to improve and optimize my ability to do predictive modeling. Now, let's talk about predictive modeling specifically. So I think of predictive modeling. I break predictive modeling down into 4 areas. First step, curation, organization, and cleaning. All right, that's getting the data from whatever the original source is, putting it together in a fashion where it can be analyzed, and then cleaning it up. You know, obviously you're going to have observations that are incorrect. You're going to have columns of data with no information in them. You're going to want to clean that up before you move on. The second part is, and where we're going to be spending our time, is preparation. Preparation is the data's ready to go, but I need to add additional structure. I need to take into consideration that I'm attempting to do predictive modeling. I need to set up the data such that I can optimize my predictive modeling approach. The third part is actually doing the modeling, obviously. And then fourth is evaluation of the model. Okay, so again, we're going to focus on this preparation step. I've talked in the past on that very first step. I've talked on the other two steps, but we're going to be in this realm of preparation. So we are going to we're going to assume that the data has been cleaned up and that we're ready to go, setting the data set up or data sets up so that we can do the analysis. All right, so again, the emphasis here is going to be on the prediction of future observations. So I know what it is I'm targeting, whether that target is a continuous variable or categorical variable or some vector of values. It's maybe some combination of continuous and categorical. We're going to assume that the data's been clean, curated, organized, and so on. And we're going to focus on 5 topics that are particular that really have an impact on predictive modeling. The first one's going to be imputation, and in a bit I will talk about what imputation is and why it's important. Data validation. Again, if you're new to data mining, this might be a relatively new term. We'll talk about this and why this is important. Sampling, feature creation, and then finally predictor. I'll say a little bit about predictor screening. Now, one of the things to keep in mind is that this is not necessarily a linear. Both the 4 preparation steps that we talked about, the 4 steps that we talked about previously, and the topics that I'm going to cover, they really aren't linear, because as it turns out, and if you've ever done any amount of data cleaning, you'll find that once you get into the data, once you do your analysis, you're going to find that there are observations that are incorrect that you've missed. You might find that there are better ways to do data validation, data sampling, feature creation, and so on. So this is even though I'm presenting this as presenting this in a linear fashion, it really is very iterative. Now, hopefully those iterative steps become shorter and shorter as you learn more about the data, but keep in mind that you might have to, at some point in time, after you've analyzed the data once or twice, go back and revisit some of these areas. All right, now I'm going to use 2 data sets for illustration. All right, these are data sets that at one time had been available on the internet. I will provide sources where I can. The first one is a fairly famous data set. It's the incidence of diabetes in Pima culture women. As it turns out, there's a large proportion of women from the Pima culture who develop diabetes. So this has been a population that's very very widely studied. In this case, a very small data set in the sense that I only have about 8 or 9 columns of data. My response is whether or not the person has diabetes. So an answer of yes is that diabetes was diagnosed between 1 and 5 years after the data was observed. So again, we collect the data, and then between 1 and 5 years later, we indicate whether or not that person has diabetes. So each row in this data table that I'm going to show you is going to be one individual. No means that in the 5 years after the observations in the data set, that person had not developed diabetes. About, like I said, seven or 8 predictors in there: times pregnant, blood glucose, diastolic blood pressure, and so on. 768 observations. As I had mentioned, a fairly small data set. This was at one time, so there are 2 sources that I like to use, and these will be provided. I assume that I'm going to be providing the a PDF version of my slides, and these sources will be available when I can, if I can provide them. This used to be available at the University of California, Irvine machine learning repository. So one of my favorite places to find data. So if you go to the University of California at Irvine's website. They've got a machine learning repository. This used to be on the website. It has since been removed, and I don't remember exactly the reason why. I had to do something with either confidentiality. It is still available on the KDD Nuggets website, which is my other favorite website for finding data. And again, those two websites, the University of California, Irvine and KDD Nuggets, I will link, at least give you the link to those websites where I can't give you the link to the actual data sets. Second data set we're going to look at is one that involves a optimization of donations to a national veterans organization. Obviously less the cost of the mailing. The idea was that, is it better to send a mailing out to everybody, or could I target certain individuals to improve, to optimize my overall return rates? This is, and again, though, if you go to the website where this data is collected, and you can find it on one of the two sources that I mentioned, they name names and say specifically not to mention those names. So I'm not going to say exactly who this is for, but it was part of a national data mining challenge. And this is, if you're not new to data mining, you might have already seen this data before. This is a fairly famous data set. Two responses of interest: donation, yes or no; donation amount, how much the person gave; 481 predictors, so quite a few columns in this data set. Approximately, the data set was split up into two: 95,000 observations for the training, about the same that you can be used for test and validation. Let me, matter of fact, what I'm going to do is, let's do this. Let me see if I can't just give you a quick show of the data. Let's do that. I'm going to give you a quick show of the data tables. So here are the two data tables. Here's the Pima data set. Again, couple of things that I want you to keep in mind is that I've got missing values in this particular data set. Here is the direct mailing data set. So let me start out. What I want to do is I want to start out talking about imputation and why it's important. So what we're going to do is we're going to look at the Pima data set, and I'm going to explain why would I want to do imputation. Okay, and for those folks who've never heard that term before, imputation is basically coming up with values where I've got missing values. So the thing that I want you to focus on in this particular example is that for some of these columns, anywhere you see a dot, in here, that's indicative of a missing value. So also keep in mind, I've got 768 observations, 768 rows in my data table. So in this case, what I'm looking at is I'm looking at a binary response, whether or not that person had diabetes. Lots of techniques I can use, but just for the sake of brevity, what I'm going to do is I am going to just look at logistic regression. All right, we're going to make it really small. I'm not going to do anything fancy. I know folks who have some modeling background, modeling understanding. I'm not going to do any feature selection. I just want to tee up why imputation might be important. So I'm going to go ahead and run that. And what we find out is that even though I have 768 observations, all right, I should only have about 300 of those observations that are used for my analysis. Let me run that one more time. All right, let me just make sure I've got this set up right. I've got my diabetes as my response. I've got my inputs. Let's go ahead and take a look. There we go. And let me just close some of these so this is not as busy. And there we go. So you'll notice that when I run this, only 392 of those observations show up. Now I could do something similar. This is done in JUMP. If I went to R and ran the analysis, I would get similar results. It would show me that I only had about 390 observations that I could work from. All right, so that's important. Keep in mind that the more missing data that you have, the sparser your data table is, the fewer observations that you'll have left to be able to do your analysis. All right, so let's go back to this whole idea of imputation. So what I want to do is I want to do something about these missing values because they could be problematic. Most analytic techniques, not all of them, but most analytic techniques do what's called case-wise deletion as their default approach. What case-wise deletion does is it removes all of those observations, all of those rows in the data table where there's at least one missing value. So again, in the extreme case, when I have fairly sparse data, I might not have any data left to analyze. So I need to do something. About it. There's a secondary issue with missing data, and that is it might cause potential model bias. And that really depends on why is the data missing? Okay. So before I get into imputation, I have to understand why or how data can be missing, because this is going to affect whether or not I do imputation, how I do imputation. So there's three groups that people typically classify missing data into. The first one is missing completely at random. So the missingness is independent of the observed data or the unobserved data. The unobserved cases or the observed cases. This is as if I went into my data set, a complete data set, and I were to randomly remove observations. So for example, let's say sometimes the doctor doesn't have time to perform a particular test, and here we're assuming that the time constraints affect the doctors equally. That might be considered missing completely at random. Easiest case to deal with, unfortunately, it's the case that probably happens the least often. It's the most restrictive case in the sense that it's saying that there's absolutely no relationship between the missing data and the complete data. The second case is missing at random. This is what probably happens most often with missingness, and that is when the distribution of the missing value is some function of what's in the data. So think of it this way: what I can do with missing at random is that I can make a statement. I can predict what's missing, the values of the missing observations, given what I already have in the data. Okay, so for example, let's say women who are pregnant more often are more likely to have an inconclusive test value. Right, there's a case where there is a relationship that exists, but that relationship has to do with information that I already have. Okay, the great thing is that if your data is missing completely at random, or it's missing at random, most imputation techniques can handle that. That's good. The problem case is that this very final case, when I've got data that's not missing at random. And that's when the distribution of the missing values is a function of what isn't in the data, what we can't see. So for example, let's say that there are certain doctors who are less efficient and they're less likely to perform these tests. That's not missing at random. So not missing at random is problematic because without any additional information, I really shouldn't be trying to impute these values. Now that said, given what I know about the data set, I may be able to use an imputation technique if I can either supplement this data or provide additional structure. So say for example, I knew these particular doctors who were less efficient. Maybe it's a function of how long they've been practicing. And let's say I had that information in the data set or I had access to it, then I could use that to determine treat this more as a missing at random and not as a not missing at random. Okay, so as I mentioned earlier, imputation is a way to fill in the missing values. You can apply it to the MCAR data, the missing completely at random, the missing at random. It's that not missing at random that you have to be careful of. And you are the owners of the data, so you should have some domain understanding. You should be familiar enough with the data to know whether something is more likely to be not missing at random or missing at random. If you don't, you can certainly, if you're like I was, an applied statistician, I'd want to go back and ask the folks that I was doing the analysis for, why are these values missing? All right. Now, let's talk about some techniques that we can employ. There's I break these techniques down into two buckets. I got simple techniques that are really one pass at the data. Let's come up with a value. And then there's what's called multiple imputation. Multiple imputation is an iterative technique, and what it's trying to do is it's trying to use some way of coming up with values that are more robust than just doing a single pass. So simple techniques. Simplest way you could probably think of this on your own, and that is what I can do is I can replace the values in a column with some reasonable measure, maybe a measure of central tendency, like the mean or the median. All right, that's one idea. There are multivariate techniques. Multivariate techniques are based on some sort of correlation between the variables, some sort of structure between the variable. For example, a very common technique is to assume that the data is multivariate normal and use that information to predict what those missing values are. Okay. There is, I think it's R-impute. There's a R-impute does this in R. Okay, so that's the simple way. That's relatively model independent approaches. Now there are model-based approaches as well. If you go out to the web, if you go actually to Wikipedia, which has a very nice website for imputation, they talk about using linear regression as a way to predict the missing values. So the idea is that you use the complete cases. You use the complete cases to predict the missing values. So in this case, I'm not going to be using the response per se, but I'm going to be using the predictor with the missing value as my response. Okay, so that's one way to predict the missing values. Second approach is that there are some iterative modeling techniques, robust to missing values. For example, there's the ways to implement partial least squares. The EM algorithm is an approach when you're doing maximum likelihood estimation, where you don't necessarily need to have those missing values predicted. There are other modeling, more complex modeling techniques. You can actually model missing values based on something like PLS as well. There are non-parametric approaches. Again, these I think of these almost as like modeling. I could use random forests to predict what those missing values are. I can use nearest neighbors or clustering. So the idea there is I've got if I want to predict a row with missing values, I find the row in the data table it's closest to, and that definition of closest is what something like nearest neighbor or clustering is going to work on. And basically you'd be using that clustering algorithm or the nearest neighbor algorithm to predict what is the nearest next observation for a given observation or cluster it falls into, and then use that to predict what the missing values are. So again, you find the closest observation in the data table, or you find the cluster that observation belongs to, and then you use that to help you predict. All right, all those approaches have been implemented. They're all relatively simple approaches. Another approach that I mentioned is multiple imputation. Multiple imputation is an iterative approach. Multiple passes are made at the data. There is not one way to do multiple imputation. There are many different approaches to multiple imputation, just as there are many approaches to simple imputation. Okay, so randomization is often a part of multiple imputation, such that you get some sort of resampling to facilitate the process. Once you're done with your multiple passes through the data, they're collected and aggregated in some fashion. And again, the way they're aggregated really depends on the algorithm that gets used. Okay, so now, one of the things to keep in mind is that a lot of these techniques are focused on continuous data, and that's true both of simple imputation and multiple imputation. A lot of distance formulas, so things like nearest neighbor relies on having the input values as continuous. So that works as long as you're trying to impute continuous values. There are a few techniques that are available that will allow you to impute categorical variables. For example, you could use clustering again to do something that I had mentioned previously, where you find the cluster, let's say an observation belongs to, and predict what those missing values might be from other cluster members. Multiple correspondence analysis is another approach that can be used to predict what those missing categorical variables are. For example, there's a package in R called MISS-MDA, and that's uses a combination of what we said earlier, the multivariate normality for continuous data, and it's using another technique. It's actually using multiple correspondence analysis, I believe, for the categorical variables. So there are some packages out there, but keep in mind then when you're attempting to impute categorical variables, missing categorical variables, that can be a bit more of a challenge. All right. There are older techniques. So if you've heard of imputation, you might have heard of things like hot deck and cold deck. The older techniques, they've sort of lost favor to the more sophisticated routines. Hot deck and cold deck were good because they were very, very simple to implement. These days, with the advent of very sophisticated computational techniques, they aren't used quite as much. All right, so here's an example. So this is what I've done is I've taken the first 13 observations from the Pima data set. I'm showing you again where the dots are. Those are the missing values. I'm only looking at the four of the columns, ones that have missing values. A simple imputation. In this case, I've replaced the column missing values with the column means. Now, what you'll notice is that the value in a given column that's imputed is the same. Obviously a drawback, because you could realize that you're not going to capture the structure of the relationships that exist between variables. Okay, so that's again, it does now that said, there are some cases where, particularly if all you have is missing missing not at random data, and you need something to fill in the holes in your data set to be able to have more observations to do your analysis. This is certainly, and it's a very simple method to implement. Second approach that I'm showing here is just multivariate normal. The assumption is that with this particular technique is that the relationship between the variables is that it's multivariate normal, and as long as that holds, then we can impute the values based on that relationship. You'll notice that in this case, the values within a column do in fact vary, and again, that has to do with the relationship that exists across the columns. And those are simple imputation. Now, for multiple imputation, again, these are just two different values. There's one that I'm showing you based on matrix completion, okay, and then there's the approach that's used, more of a Markov chain Monte Carlo approach that's used by the mice package in R. Both cases very simple. The middle case is implemented within jump, very simple, point and click. The case on the right is implemented within R, very simple, just specify, here's the data set that I want to, with the missing values, so I want to impute. And that's my values. And again, I'm going to use these. I'm going to use these values with the new values in my going forward to be able to circumvent the issue with the cases or the case-wise deletion. Okay. So advantages and disadvantages. Obviously, with a simple case, easy to implement, simple to understand, computationally very fast. Disadvantages is you just might not capture the structure sufficiently well and bias your results. Multiple imputation, flexible, robust, can be difficult to explain and implement, can be computationally slow for very large data sets. So again, something to keep in mind. Okay, I'm about halfway through my time. I didn't see any questions in the chat. I'm going to stop there for about 1 minute, and if there are any, I'm going to say if there are any questions, um, please type them in the chat window. Otherwise, we can move on to the next section, which is validation. Okay, I'm gonna go ahead and move on. But if you have questions, please type them in the chat window, and then and I'd be happy to answer them. So imputation, that's the first of the 5 topics. Second topic I want to talk about is data validation. So one of the issues with predictive modeling is that I'm often going to rely on a modeling technique that's very, very flexible. With a very flexible technique, one of the things I need to guard for is that I am going to be overfitting the data. Think of that in another way. What I'm attempting to do is I'm attempting to uh, apply structure, create structure where there is none, or trying to model noise. So what's to keep me from doing that? There are techniques, neural networks being one of them, that are so flexible that without any safeguards, I can fit a perfect model. So it fits a perfect model. However, it's not extendable to new data, and that's what I'm trying to guard for. So the solution, if you go to just about any predictive modeling, any data mining textbook, is we're going to split the data up. And we're going to split the data up in either 2 pieces or 3 pieces or many pieces. All right, let me start with the first 2 cases. I'm going to hold back part of the data. I'm going to use part of the data to actually build my model, and I'm going to hold back part of my data either 1 piece or in 2 pieces. All right, so I'm going to build that model on the training data set. So that's one of my parts. If I only break it up into 2 parts, I'm going to have this validation section. And this validation section can be used to tune the data set. All right, by tuning the data set, what we do is we think of it this way. I start with a very simple model. I continue to add structure. I continue to add features to the model, all along checking how well the model fits on my validation portion. So at some point, the fit statistics between my training data set and my validation training set diverge. And that's at the point where I start to consider stopping my modeling. So stopping adding structure to the data because I'm starting to overfit the data. So that second part can be used to do that. Second part can also be used as a test. So basically, that testing is just I'm fitting a model to the data, and then I'm done with the model, and I apply my model to my test portion to see how well it fits. Obviously, there's benefit in having that second portion in there because I know when to stop. However, one of the potential issues with having only a training data set and a validation data set is that I still might get an optimistic estimate of how well my data is fitting. That's why, as I had mentioned, sometimes it's nice to have that third set of data in there because it provides an independent check on how well the fit is. So again, the training data set is used to actually build the model. The validation set is going to be used to tell me when to stop adding structure to my model. And then the test is just independent of both of those other 2 portions, and it's just applied to the final model to see how well things fit. Now, how much data do I need? It really, a big question. I always get asked that. And it really depends on how much structure there is in your data and what you're trying to predict. Sometimes a few hundred observations is enough to split your data into 3. Sometimes you need a lot more. It really depends on how complex the data is and how complex the relationships between your inputs and outputs are, what modeling techniques you use, and so on. So it's impossible to say out of context how much data you need. But this, again, this is a very common thing to do, and there's some variations that might be helpful when I start to have too little data to capture the structure in 3 parts. Okay, so I talked about holdback. Basically, we'll talk a little bit about bootstrapping, which is one of those techniques I can apply to my data to leverage some of the iterative techniques, and then k-fold, which is one of the extreme techniques in the sense that I can use k-fold with very, very small data sets. All right, so holdback, we've talked about this. We split the data in either 2 or 3 parts. The goal, the important thing here to keep in mind is that when I split my data like this, I assume that each part is representative of the same population. Okay. If I can do it randomly, that's fine. I just randomly assign each observation to one of my groups. What proportion should I spread them out as? Another question I often get asked. I've seen a lot. I have not seen a definitive answer. Obviously, it's going to depend on the complexity of the data. I've seen cases where the data is split up. Half of it is used for training. The other half is split between testing and validation. I've seen it more heavily weighted towards training portion and a lower weighting between the testing and validation, and I've seen it split equally. So really, the nice thing is that I think all of these should be tried, and this is also hints at, well, if I do this in an iterative fashion, if I bootstrap this, I might come up with a better measure of my models and better understanding of how good things are fitting. The other thing to keep in mind is that in some cases I want to do some sort of stratified sampling. So in this case, I believe that I might believe that within strata, representation is a bit different than across strata representation. This might happen for a time-dependent case where data from 1 week might be different from data from a second week. So I probably want to split my data up so that I've got an equal representation in test, training, and validation, or test and validation for each week. This is particularly useful in the cases where there is imbalance between the strata. So I might have I might have a lot fewer observations from 1 week than another week, and I want to ensure that I get equal representation. And we'll talk a little bit more about imbalance too, because that might affect how well the modeling does. But stratified random sampling is also something to keep in mind. Again, if you think that there's differences between the variability, the representation within the strata and across the strata. Okay, and then another technique that's often applied is some sort of clustering to determine what the strata are. For example, if you're let's say you're developing a marketing campaign and you want to apply that marketing campaign across different customer segmentations, you might do something like cluster analysis to determine, well, what's a reasonable representation of my customer segments, the population that I'm going to try to target. All right. So variation on this is bootstrapping. So holdback is just one pass. With bootstrapping, I sort of get the advantage of being able to do what I just said previously with smaller data sets. So it's an iterative technique, and at each iteration, the data is repartitioned, either randomly or with stratification. And then what I do is I collect my fits at each step to see how much variability I have, to see how well my models fit. So that's a technique as well. One variation on this is to weight the observations, changing the weights at each iteration. Now, I can't go into a lot of detail on how this is done and why this is done, because the weighting schema in this particular case is particular. And I will reference this paper. I do reference this paper at the very end of my talk. And the technique I'm going to be talking about is due to Wu-Booz and Stefanski. Okay, so in this case, I have seen it applied to data sets as small as a few dozen observations. So again, very small, particular way of approaching it, but it allows me to leverage these techniques with very small data sets. The final iterative technique I want to talk about is k-fold. This is sort of the extreme. All right, so now with k-fold, what I do is I split my data set up into k equal or nearly equal parts. Then what I do is at each iteration, I hold out one of those parts for validation, and then I use the remaining parts to build the model. I keep on going until each of my folds is held out of the data. And then at the end, what I do is the final model gets picked from my group. I use some weighted average. There's different things that I can do. Again, implemented in most software packages. I saw implementations of how you do this in R. So very, very common technique. It's great for very small data sets. One of the difficulties, though, is that it may have a tendency to overfit the data because obviously you're using all the data to build the model. All right, you're using all the data to build the model. Certainly, if you pick the best out of your k folds, then you might you're cherry picking and you might have overfit a bit. A typical choice of k is between 5 and 10, so split the data set up into 5 or 10 spots. In the extreme, there's something called leave one out, where I basically leave one observation out, use the rest of the data to build the model, and I iterate till each observation is held out once. Very good for really, really small data sets. Again, the issue here is that there's potential for overfitting. All right, I talked a little bit about sampling. I'm going to re-investigate sampling. We talk about sampling in the context of ensuring representation of my validation parts of the partitions that I split the data into. And again, clustering can be used to do that. What I want to focus on, what you might not have considered sampling for, is that in the case when I have class imbalance, that is, if I look at my response, let's say I've got a binary response, and the category that I'm interested in predicting, the level that I'm interested in predicting, has a low proportion of values, then I've got class imbalance. If we go back to the direct marketing data set, we'll notice that of the 95,000 observations, only about 5 of the observations actually returned a donation. So very large class imbalance. Okay, so that's a case where I really need to be careful, because without some sort of sampling, without some sort of weightings, anything that I can do to address the class imbalance, the prediction is easy. Nobody's going to return a donation. But that's really not what I'm after. I'm really after predicting what are the characteristics associated with returning a donation or returning a donation of a certain value. Okay. The other time when class imbalance might occur is that often what people will do is they'll focus. So for example, if it's a continuous response, what people might do is focus on a portion of the population. They might look at the first decile or the 10th decile. All right. So for example, with the direct mailing case, if I focused only on the 10th decile of donors, they returned as much in donations as the bottom 50% of the data. So rather than focusing on the entire set of donors, I might want to focus only on that top decile or the top 2 deciles. So again, that would cause class imbalance, though, and I would need to take that into consideration. So how do we handle this? There's 3 techniques. There's 3 ways I can handle class imbalance. One is to oversample the data. By oversampling, all I'm doing is I'm generating observations, either through resampling the data or through coming up with some way of simulating new values. So for example, with the direct mailing, I've got 90,000 non-responses, 5,000 responses. I would somehow generate 90,000 more responders, donators. Obvious disadvantage there is that it artificially inflates the sample size or makes assumption about the structure of the data. Plus, you need to come up with a technique to do the sampling if you want to use something other than the sampling with replacement. So a little bit more complex to implement that. Undersampling is another approach. Undersampling is just the opposite. I just sample fewer observations from the non-target level. So again, with our direct mailing, I've got 90,000 and 5,000. What I would do is I would randomly sample 5,000 people from my non-donators and compare those to the donators. Now, the disadvantage here should be relatively obvious, and that is I have to make sure that the 5,000 that I sample really capture the structure of the non-donators. All right, simple. So undersampling, much simpler to implement. Make some more assumptions about what it is the level that I'm undersampling from. Now, one of the ways to get around this is to use the bootstrapping that I had mentioned earlier. Is that we can run this model numerous times. We can fit a model to the same 5,000 donators, but randomly select 5,000 non-donators and iterate over that, however many thousand times, 10,000 times. That's an approach. That's one way to get around the undersampling issue. A third approach, and this is good when it can be implemented, and that is to put a higher weight on the target level. Now one way this is often done is by assuming that there is some cost or profit associated with misclassification. All right. So, for example, I know how much a mailing costs in my direct mailing. I know how much, let's say, the average or median donation is. I can assume that if I misclassify a donor as a non-donor, I'm going to lose some measure of the donation, let's say the average, just to be simple. However, if I misclassify a non-donor as a donor, my cost there is just the cost of the mailing. So I can use that as an explicit way to weight my values, to weight my imbalance. So that often is very helpful. And again, this is helpful in those cases where I have something that's a little bit more explicit, where I can actually associate a cost with the misclassification. All right. Two more topics I need to talk about. I've got about 10 minutes left. Feature creation is probably this is another one of those cases where there's a lot of art that's involved, in the sense that you have to understand your data. So what you're attempting to do with feature creation is to create columns in your data set that capture relationships between the predictors and responses that wouldn't necessarily exist or wouldn't be recoverable by the modeling technique. So I could do that by either adding features using existing data, or I might have to go back and add external data. I can aggregate columns or levels in a column, or I can disaggregate, basically break a column up into multiple columns. There are transformations, take the log of a column, take some sort of function of additional columns. And then finally, I can look for latent structures. And that's using something like principal components or some sort of latent structure technique like PLS that allows me to create latent structures. All right, so as an example, if we were to go into the direct marketing data, there's a variable in there, RAMNT, and that's how much donation was made at each mailing. The way the data was collected is that there were 24 mailings over a 2-year period. In addition to the current mailing, which was what was attempted, what we're looking to predict. So there's 24 columns in the data table that indicate how much was donated for that given mailing. So if I were just to approach this using a technique like one of the tree-based methods, a linear modeling technique, there are certain structures that wouldn't necessarily be captured. For example, a person who donates a certain number of the last mailings. I might posit, again, let's say I knew a lot about this data, I might think that a person who is going to donate a lot is going to donate at least N out of the P mailings, or fewer than N out of the P mailings. So again, but that information is not captured in the data. That would be something where I would use these 24 return amounts variables to create my new feature. A person who donates at least so many dollars for one mailing. A person who's made a large donation more than P mailings ago. Again, the thing is, I might assume that a person who's going to donate a large amount is not going to do that on a frequent basis. But if they have donated a large amount more than 10 mailings ago, then maybe it's time for them to give another donation. Again, these are things that this is where the art comes in. You have to understand what are the characteristics of the data that I might be able to create that would help me predict my value, the number of mailings a person has received over this period, and so on. Okay. Focusing on the zip code variable. So one of the variables in the data set here is zip. I might want to pull in information such as the median income by the zip code. I might feel that, well, if you come from a richer zip code, you might be more likely to donate more often or more. So the zip also gives me a good segue in terms of the idea of aggregation. So aggregation occurs when I'm taking either multiple variables and putting them together, or a multi-level variable and trying to reduce the number of levels in the data. One of the advantages of aggregation is that it makes things go faster, which for very large data sets could be helpful. And we saw an example of this previously. I can combine binary variables to get counts, or continuous variables to get totals. I can combine levels of categorical variables, and I can do that based on convenience. So example for the zip codes, I could just look at who comes from where and combine all of those cases where I have only one or two observations from that zip code. I could use intuitive appeal. I can turn those 5-digit zips into 3-digit zips, or I can use some sort of perceived relationship. And this last bucket is where you might find a little bit more benefit. And that's because what I'm doing is I'm using some sort of technique, some sort of modeling technique to be able to say, well, where are my high income zip codes? Let me put those into one bucket. Maybe I can put them into quantiles, or I can put them into deciles, and I can use that rather than using the zip codes. I can use the quantiles as a way of modeling the data. So one of the things I need to point out, and I think this is really important, one of the difficulties, one of the problems with categorical predictors that have a large number of levels, in particular with some of the tree-based techniques, is that they have a tendency, regardless of having a validation holdout, they have a tendency of over-predicting. Because there are so many possible combinations, it's easy to come up with combinations in both the training, validation, and maybe even the test set that actually fit really well. So one of the ways to circumvent this is to turn a column that has maybe 1,000 or 2,000 levels to something that's got a lot fewer. In the direct mailing data set, I think there are 17,000 different zip codes. So it is beneficial to combine those. So disaggregation is just the opposite. Disaggregation is when I split up a variable. Honestly, I think of this more as a what happens before preparation. This is this is a case where I've got a column, and that column really can be split out because of the characteristics of the column. The RFA variables in the data set, the direct mailing data set, it could be split up into a recency, a frequency, and an amount, and it's just the way that that variable is created. And then real quickly, transformations are exactly that. Two common general approaches to transformations are the Box-Cox and the Johnson family. There are a lot of techniques, however, that are much more robust to the lack of transformations. Things like neural networks, because it's a nonlinear technique that already does a nonlinear transformation on the data. The tree-based methods are fairly robust because they're non-parametric. They're not fitting an underlying parametric model, and sometimes these types of techniques can capture some of the things that transformations are trying to circumvent. Standardization is one of the common techniques that's used for transformation. It's basically centering your data at 0 and scaling it by the standard deviation. And the advantage, even if this doesn't help from a modeling standpoint, one of the advantages of standardization is that everything is on the same scale. Yeah, and just a caveat, if you got outliers, hopefully you've taken care of them in the pre-processing, the pre-preparation step, because these can affect your transformations pretty severely. All right, I've got about 3 minutes left, so let's do this. Let's really, very, very quickly, I wanted to talk about feature creation. Feature creation we end up with feature creation. There are multivariate techniques to find latent structures. I didn't talk about that. Principal components analysis, partial least squares are good for continuous variables. There are some techniques that can be used for categorical variables in terms of reducing dimension. And again, here the idea is that the fewer columns in the data set that I have, the more computationally efficient my modeling problem is going to be. So I list some of the categorical approaches. And again, variable reduction and aggregation, often they can be used together. Computationally difficult, it can be very time consuming. So what I wanted to end up with is predictor screening. I know that we're almost up on the top of the hour. So predictor screening is basically removing columns from your data set or coming up with those important columns. So finding good predictors, that's usually what people think about when they think about predictor screening. This is good for relatively simple problems where I need a quick answer, and I'm going to use a fast technique such as random forest to come up with a set of columns that might be good predictors. And then if those set of columns help me predict well enough, then I'm good to go. So that's usually where people think of predictor screening. However, it's also important when it comes to removing unhelpful predictors. So I'm just using the flip side of what I would do finding good predictors. Rather than picking the top 10, I might get rid of the bottom 80% or so, depending on how much each of those columns contributes to my prediction. Okay. So there are things that you could do at the data cleaning step that help you facilitate some of this predictor screening. Removal of predictors with a large proportion of missing values or variability close to 0. Again, random forests can work really well in terms of finding unhelpful and helpful predictors. All right, so we are just about at the top of the hour. Couple of different, I'd mentioned the Wooboos and Stefanski paper. So there's the reference to it, and I assume that these slides will be available. A couple of books that I find really helpful and a couple of websites. Elements of Statistical Learning, that's sort of the standard text that is referenced when it comes to data mining. It's, I think it's the second edition that's out. You can find it on the internet. It can be very, very technical, however. So if you don't have a statistical background, mathematical background, there'll be some challenging parts. Even if you do have a statistical background, there are some challenging parts. I mentioned two general data mining or predictive modeling books that I like. There's many more out there. These are two that I seem to reference a bit. There's the Data Mining with R, it's a case study based approach, and then there's the Kuhn and Johnson Applied Predictive Modeling. good books. If you don't have books on data mining, check them out. They do talk about some of the things that I had mentioned as well, which is a nice thing about the books. And then the two websites that I had mentioned. I'd mentioned the KD Nuggets website and then the UC Irvine Machine Learning Repository. Okay, so I'm going to stop there. We are right at the top of the hour, actually 1 minute over. I'm going to stick around if there are more questions. So I'm going to turn it back to you, Steve.
Hey, well, thank you, Don. I certainly learned a lot from the presentation, and many terms I thought I knew. I learned something significant today. So if you have any questions for Don for the next few minutes, we can have you send them via the chat. If you want to reach out to Don directly with your questions, we can do that. This recording will be made available on the Statistics Division YouTube channel once I get it processed. And if there's anything else come up. So now I got some questions. So one question early on was, what about people who died after 5 years? So no diabetes data. And then would that be NMAR?
Well, the way that the data was collected is that there was one point in time where the observations were made. Let me go back to the here. Okay, so let me go back to the data. Let me go back to the diabetes data. So we're looking at the diabetes. So these observations, the times pregnant, blood glucose, BMI, diabetes pedigree, they were made at one point in time. For anyone who showed positive for diabetes, that meant that after 1 year, but less than 5 years, that they developed diabetes. The idea was that to throw out those observations where a person developed diabetes in the first year because they would have been too easy to predict. All right. So for the folks who did not have diabetes, what that meant is that between the time period 0 and time period 5 years from the observations, no diabetes was presented. If a person died after 5 years, they didn't have any data on them. I mean, that was basically, the study was ended after 5 years, after the data was collected.
Okay. And then another question, can you create the predictive model with the missing data, then next run the model with the imputation values, and then compare the two models and see how they perform?
Absolutely. I mean, I would do that. That makes perfect sense. I mean, just see. I mean, you're going to have to ask yourself, though. I mean, which one is does the well, actually, two things. Does the I mean, which model is more representative of the underlying data? I mean, you can have a situation where that missing data is biasing your results. Likewise, you can have a situation where the imputed data, because you really had missing not at random, that imputed data can be biasing your data. But I mean, I think given that computation is cheap and that it's relatively fast, it does not hurt fitting both models and seeing if they're close, to seeing if one has much more predictive power. And if one's going to have more predictive power, it's going to wind up being the model with the imputation, just because you're going to have more observations in the data and you're going to have a little bit more power. So, but I would encourage people to do that. I think that makes perfect sense.
Well, thank you, Don. That was it for the questions. Again, thank you to all that participated in today's webinar. We have another one scheduled in early October. It won't be as statistical. And then we're working on a few more for the rest of this year. So look for the Statistics Division e-zine with the announcements and the registration. So with that, I thank Don again, and I thank you all for attending.
Thank you, Steve. Thank you, everybody.